Hello. What I want to talk to you today is about something that took me a little while to figure out. Not for any sort of reason because it's difficult, just because it's maybe a obscure topic, perhaps. Zifwell uses it in his book on reactor physics, and what I wanted to talk to you about is the idea of this conversion. If you were to have a incremental volume in three-dimensional space, this can be expressed in terms of the square of the dimension times the differential value du times some sort of solid angle d omega. So we're expressing this volume here, du, in terms of u and du and omega. And u here is the sort of the distance away from the origin, wherever that is. So how do we go about this sort of conversion, you could call it? Let's talk about the differential angle, or maybe the definition. Let's go with that first. Let's call it the definition of the radian. If we have alpha radians, this is just equal to the length over the radius, where the length being counted, if we have our unit circle here, or it's not really a unit circle, it's more of a circle of radius r. Our length is the length around this guy here, and r is this angle alpha here. We're subtending from here to here, for example. This is going to be alpha radians. We can express this in differential form as alpha tends to 0, as L tends to 0. We can say d alpha by, this is where the limit of we can say L approaches 0. Excuse my terrible writing there. The limit of L going to 0. D alpha here, this is just equal to d L by r. R stays constant as L goes to 0. The two-dimensional, or maybe you can call it three-dimensional, counterpart to this is the notion of the solid angle. And the solid angle is, if we were to have our unit, or our sphere, some radius r, and some sort of area subtended on it of area a sub n, for the area normal to the sphere. We can write the solid angle as solid angle omega just equals the area subtended, or a sub n, over the radius squared. And as the limit as a approaches 0, that's just going to be our solid angle subtended will shrink to an infinitesimal volume, and we can express it like this. Okay. Or if we're using the notation from before, we can, or the notation employed in Zipf-Wells' book, we can write d omega, another omega, equals d squared u by u squared. D squared u here is our characteristic dimension. So we can rearrange this guy. So go ahead and rearrange this. Just move this guy over here. Oops. We can take this guy and rearrange him. And we can say that u squared d omega is equal to d squared u. Okay? Starting from this point, in fact, let me just go ahead and start a new slide here. Oh, that didn't copy over. Sorry, let me just rewrite this real quick. We were at u squared d omega equals d squared u. If we were to sort of draw this out, we have some sort of distance u, and we'll have some sort of like area measuring du by du, and it's subtending the solid angle d omega. Okay. If we were to take this and we were to draw it on a sort of side view, we have du here. Now if we were to expand this by a factor of du, now we have our cube, du by du by du, as I mentioned in the start of this video. So in effect, if we multiply both sides here by du, then we're expanding this out to a cube, and likewise here, we're expanding that out into a three-dimensional volume. So we can write u squared d omega du equals d cubed u. So that's where this comes from. I hope that's insightful for you. It took me forever to figure that out. Finally found it in some sort of obscure book on heat transfer. What else do I want to say about that? The other thing I guess I could say is maybe you might want to imagine that there is a bit of a problem with this sort of derivation, in that if you have a closed surface and a solid angle d omega subtended by the surface, this is a side view, as sort of the rays subtend further outwards, extend further outwards, not subtend. This area here is less than this area here, but you can sort of get around this technicality by the fact that this distance here is just du. It's an infinitesimally small length, so it doesn't really matter too much that in fact this area is larger than this area, because it's only an infinitesimally small amount larger. The extended surface is only an infinitesimally amount larger than the original surface. we can put it that way. And from what I recall, but I didn't make a note on this, so I have to think about this for a second. From what I recall, there was a similar sort of argument about the infinitesimal annular ring. From what I recall, when you worked out that differential area, it reduced down to whatever it did reduce down to, because the infinitesimals multiplied out or something like that. Maybe I'll do a video about that another time, but really that's all insignificant, immaterial with respect to what I wanted to talk about, which was this here. So thanks, and next time I hope to get to a bit more reactor physics.